Alright, what's up guys? In this video we're going to pick up some differential equations. We're going to be talking about second order non-homogeneous ordinary differential equations. So we're asked to find the general solution to the second order non-homogeneous ordinary differential equation using the method variation of parameters. So we're given the non-homogeneous equation y double prime minus 2y prime plus y is equal to e to the t over t squared plus 1. Alright, so define the general solution to the second order non-homogeneous ODE. Recall that we first need to find the complementary solution, which is finding the general solution to the homogeneous second order ODE. And then we need to find the particular solution. And again, we're going to use the method variation of parameters. There's two ways typically to find the general solution to a second order non-homogeneous differential equation. The first way is, of course, the way that we're going to do it today, which is variation of parameters. The other way that you can do it is by the method of undetermined coefficients. So here is the method variation of parameters that we're going to use here, and I have done videos on this before, so this isn't the first video I've done on using this method. I also have videos on how to do the method undetermined coefficients, but in this case we'll focus on variation of parameters. So what we want to do is we're going to first need to obtain the solution for the homogeneous equation. And remember, it's homogeneous because it's equal to 0. So the form for that will be ay double prime plus by prime plus cy is equal to 0, or y double prime plus q of ty prime plus r of ty is equal to 0. And we obtain the general solution to the homogeneous ordinary differential equation by finding the roots. The solution form, or the solution will take a certain form depending on what kind of roots we get. So if we get real and distinct roots, it'll take a certain form. We get complex roots. If we get repeated roots or double roots, it'll take the general solution take a certain form, and so that will be the general solution for the homogeneous equation. And then we will need to obtain the particular solution, and the general solution for the non-homogeneous ODE using variation of parameters will be a combination of the complementary solution and the particular solution. And for the particular solution, we're going to use the method variation of parameters, which involves doing these kind of ugly integrals. Now, how hard the integrals are to deal with depends on the problem. In this particular case, they shouldn't get too nasty, but again, we won't know to actually get through most of it. Okay, so the first thing we need to do is go ahead and get the complementary solution. So let's get that out of the way for the homogeneous equation. So that's the first thing we need to get. So we need the complementary solution. And again, that requires us to solve the homogeneous equation, which takes the form, again, y double prime plus q of ty prime plus r of t y is equal to 0. So we need to get the auxiliary equation, so let's get that, and we'll find the roots. Okay, so what's the auxiliary equation here? Well, first of all, let's rewrite this as a homogeneous equation, and then we'll write down the general solution and put that over there. So as a homogeneous equation, we write this as y double prime minus 2y prime plus y is equal to 0. So we need the auxiliary equation now. So the auxiliary equation here is going to be r squared minus 2r plus 1 is equal to 0. That's the auxiliary equation. Now we need the roots. So what we're going to do is use the quadratic formula. Sometimes you can factor, but we'll use the quadratic formula in this case. Quadratic formula always works, although factoring is the easier way. So the quadratic formula, that's a negative b plus or minus the square root a b squared minus 4ac all divided by 2a. So a here is 1, b here is negative 2, and c here is obviously going to be 1 as well. So what we'll end up with is negative 2 plus or minus the square root of b squared minus 4ac all over 2a. So this would be negative 2 squared minus 4 multiplied by 1 multiplied by 1 all divided by 2 multiplied by 1. We take care of the discriminant, which is everything under the square root, which is negative 2 squared minus 4 multiplied by 1 multiplied by 1. This obviously gives us the square root of 0, which you know is 0. Once we take care of the discriminant, 2 times 1 is obviously 2. So what we have, we're gonna get repeated roots, but just to prove it, we'll have negative 2 plus the square root of 0 all over 2. And then we'll have negative 2 minus the square root of 0 all over 2. And clearly, we're just going to get r. Now, r is going to be equal to 1, but there's going to be a multiplicity of 2. Of 2 here. Both roots will be 1, so we have a multiplicity of 2 for the roots. So that's the first thing we need to do, is we need to circle that. Alright, now remember, as I said at the beginning, the solution will take a certain form. The general solution for the homogeneous equation will take a certain form depending on what kind of roots you get. So since we get repeated roots or double roots, if we, and I'll go to another sheet because we're going to run out of room. Recall that if we get repeated roots, or double roots, the general solution will take the form y of t is equal to c1 e raised to the r t plus c2 t e raised to the r t, where c1 and c2 are arbitrary constants. So therefore, the general solution, or the complementary solution in this case, for the homogeneous equation for us is just going to be yc of t is equal to c1 e to the t plus c2 t e to the t. So that's the complementary solution, or the solution to the homogeneous equation for us. All right, so that's taking care of part 1. So that's the first thing that needs to be done. So if you don't know how to do that, I do have plenty of videos on that. So it requires you to first find the auxiliary equation, which we did. Find the roots. Again, solution form depends on what kind of roots you get. In this case, we got repeated roots or double roots. So we know the solution takes the following form. We ended up getting r is equal to 1 with a multiplicity of 2. So again, the general solution here is just, or the complementary solution in this case, will just end up being yc of t is equal to c1 e to the t plus c2 t e to the t, where c1 and c2 are arbitrary constants. Okay, so that takes care of part number 1. The next step is to find a particular solution, which is just us using the method variation of parameters. So now we need the particular solution, and we're going to get that next. Now, let's go back to the formula for the variation of parameters. Recall that the W of the W of y sub 1 comma y sub 2, that's the Wronskian, and I have plenty of videos on how to find the Wronskian determinant. And recall that for the particular solution, particularly in this case when using the variation of parameters, it doesn't make a difference which we pick to be y sub 1 and y sub 2. It just does not matter. It doesn't affect the solution at all. So what we'll do is we'll determine what y sub 1 is, y sub 2 is. We'll need to compute the Wronskian, and then we have to plug all that stuff into this integral, and we'll see how nasty it gets. Hopefully it doesn't get too bad. So let's get y sub 1 of t. It doesn't make a difference which one, but in this case y sub 1 of t would just be e to the t, and then y sub 2 of t will be te to the t. Now we need to compute the Wronskian. We need to get our Wronskian determinant. So recall the Wronskian. It's just basically a matrix of those. We have our functions, which will be y sub 1 and y sub 2. What we'll need is the first derivative of each of those. So we'll need y prime sub 1 and y prime sub 2, which would just be the first derivative of each of the functions. And then we'll compute the Wronskian determinant by cross multiplying. So we'll have, hopefully you remember how to find the determinant of a 2x2 matrix. That's pretty much the same thing. We'll do a times d minus b times c, and that'll give us the Wronskian. So we'll have w y sub 1 comma y sub 2. In our case, we plug in our functions. So we have e to the t, and then we got our second function, which is t e to the t. We need the first derivative of both of these. So the derivative of e to the t is e to the t. Then we need the derivative of t e to the t. Obviously, this is with respect to t. And so we're going to have to apply the product rule here. And if we apply the product rule, we'll get e to the t plus t e to the t, which is the derivative that we get for that function. And then we compute the Wronskian determinant, which is, again, hopefully you remember, it's the determinant of a 2x2. It's going to be this times this minus this times that. So that'll be e to the t multiplied by e to the t plus t e to the t. And we'll subtract that from e to the t multiplied by t e to the t, or t e to the t times e to the t. Doesn't make a difference. Same thing. Multiplication is commutative. So if we simplify this, we see what we get. Well, it looks like we're just going to get e to the 2t here. When we compute, when we do the multiplication, that should be correct. So the Wronskian here that we end up getting is going to be e to the 2t. Okay, so that takes care of the Wronskian. The next step here is now plug all this information into that variation of parameters formula, just here. All right, so we just got to follow the formula here. So again, this is the particular solution that we're getting now. We already have the complementary solution. We got that earlier. So it says that it's going to be negative y sub 1. So that's going to be negative e to the t. Then we got the integral. And we got to plug in y sub 2 times g of t divided by the Wronskian. Don't forget about the fact that when we go back, that we had e to the t over t squared plus 1. So there's another e to the t up there, so don't forget about that. And there's also a t squared plus 1 down at the bottom. So we're going to forget about that stuff. So it looks like what we'll end up with is t e to the t. We still got an e to the t that was on top, remember? And then down here at the bottom, we'll have our Ronskin, which was e to the 2t, multiplied by t squared plus 1. Now it's going to be dt. This will be plus, and then we'll need to pull out, we'll need to have our y sub 2, which again was te to the t. So this would be te to the t. And then we got our integral, and it's going to be y sub 1 times g of t. And you could think of the g of t as just being e to the t times, or excuse me, e to the t divided by t squared plus 1, because that's what our g of t was, recall, when we go back to our question here, that's what it was. So we got to plug all that stuff in. So in this case, it looks like we'll end up with e to the t times e to the t, and that's going to be all over our Ronskin, which is e to the 2t, and then we still got the t squared plus 1 down here at the bottom. So this is what we get so far. I actually prefer doing variation of parameters over undetermined coefficients, but everybody has their favorite. I just prefer the variation of parameters. Maybe it's a little bit different. Maybe you're different, don't like that variation of parameters, but I prefer this over undetermined coefficient. So we just got to clean it up here. So you stay at the constant on the outside. You kind of think of it just kind of like a number. And we do the simplification. Well, it looks like we're just going to end up with a t on top. And then we'll have t squared plus 1 in the denominator. That's with respect to t. Then over here, again, we're not really concerned with this te to the t right now. It's a constant. It's out front right now. We're not concerned with that. Then we clean up this side over here. Okay. Well, if we clean up this side, we'll just end up with 1 over t squared plus 1 dt. So now we got these two integrals to deal with, which are very easy to compute. We know we're going to get the natural. Well, this is going to be, well, actually, since we have a negative e to the t on the outside, this actually ends up being negative 1/2 e to the t ln absolute value of t squared plus 1. We can actually drop the absolute value bars, which we will. But that's what that'll be. And then this is just going to be arctan. But let's just go through the whole process if you don't know how to integrate these. So we got negative e to the t. Again, imagine we're treating that as a constant. And then we got t over t squared plus 1. So if you don't believe me, let's show how. Do a u substitution. Select u to be t squared plus 1. That means that du is 2t dt. And so what happens is we end up getting, after we do the simplification, we pulled the negative 1/2 out front. Well, I brought the negative to the front. Then we still got our e to the t, because again, we're treating as a constant. And this is the integral of du over u. So again, this gives us negative 1/2 e to the t ln absolute value of the u plus c. So we put the u back in. We can drop the absolute value bars. So this would be negative 1/2 e to the t ln. And then we could drop the absolute value bars, and it'd just be t squared plus 1. You don't need the plus c, but just kind of being technical, it would just be plus c. Just if you want to be technical with it. You don't need the plus c, though, in this particular case, since we're doing variation of parameters. So that's how you get the antiderivative for that part, if that part wasn't making sense. And now the next part was, if we go back, we need to integrate 1 over t squared plus 1. That's arctan, remember? Hopefully that's something that you remember. Now we do have the te to the t on the outside there. So in actuality, we got te to the t, and they got the integral of 1 over t squared plus 1 dt. So in actuality, this is just going to be te to the t, and it'll be tan to the negative first, or arctan, depending on how you choose to write it. And that's what that would be. So we've taken care of both of the integrals, and as you can see, they didn't get too nasty. So when we did the integration for both pieces, for the first part, again, we can take the plus c's off, but I just kind of put them there just to be a little technical with it. And that's what you get when you deal with both the integrals. So they didn't get very nasty, which is great. They won't always be that way, so just be aware of that. Okay, so remember with the variation of parameters, we take our general solution is going to be a combination of the complementary solution and the particular solution. Now we gotta write down our particular solution first. So the particular solution in this case, okay, it's going to be negative 1/2 e to the t ln. We can drop the absolute value bars. It'll be t squared plus 1, and then it'll be plus t e to the t arctan, or tan to the negative first of t. So that's the particular solution right there. So the general solution is just a combination of this complementary solution and this particular solution that we ended up getting earlier. We'll go back to the example that we did earlier. So the complementary solution was this, because we got repeated roots, and the particular solution is what we got here. So the general solution is a combination of both of those. So let me circle our particular solution. Always like to circle with the red marker, just to make sure that we're all on the same page and nobody's lost. So that's the particular solution. So now we write the general solution, which is a combination of both. And that's the solution. So these types of equations are a little harder to solve because there's more work that's needed. So general solution here is y of t. It's going to be a combination of that complementary solution and our particular solution. So therefore, our general solution for this non-homogeneous equation will be y of t is equal to c1 e to the t plus c2. Again, these are c1, c2 are arbitrary constants. Te to the t minus 1/2. Now, why is it minus? Because, again, we got negative here. So it's going to be minus 1/2 e to the t ln. Again, we drop the absolute value bars. We don't need to keep those up. Be t squared plus 1. And then this will be plus t e to the t. Then it'll be arctan, or tan to the negative first, depending on how you write it. And then that'll be your solution, your general solution to the homogeneous equation. And that is your answer. So as you can see, it took us a little bit of time to get through this problem, but that's pretty much how you do it. So each of the ways, whether variation of parameters or undetermined coefficient, each have their uses. Just depends on, it just kind of depends on which one you like, and that'll kind of determine which one's easier. Alright, so that's a variation of parameters. Alright, so let me know if you guys got any questions. I'll be more than happy to talk about it with you, and I will see you guys next time.